recall, suppose I've got two functions. Let's make them go from the naturals to the positive reals, or non-negative reals. If I write like f, and let's say that, and c is a real number. If I write f is equal to c plus little o 1 of g, what I mean is that the limit as n goes to infinity, I got to get this the right way around. So f of n over g of n is equal to c. We might not have technically introduced this before. I might have just had with a 1 plus little o 1, but it's hopefully kind of natural. If it's a c, then it just means this. So let me restate this Erdős theorem from last time. Well, I stated it last time. We're going to prove it today and Tuesday. So Erdős theorem. It says if H is a graph, with at least one edge, which we could also write as chromatic number is at least 2. Then the asymptotics of the extremal number, so the extremal number ex n h, remember that's the maximum number of edges, n vertex graph with no copy of h. There's going to be a slight difference in how I write it this time than last time. There was actually a small error last time. So I'm going to write this as chromatic number of h minus 2 over chromatic number of h minus 1 plus little o 1 times n squared over 2. So here's the error. Last time I wrote this, so 1 plus little o 1 in the front, chi of h minus 2 over chi of h minus 1, and then n squared over 2, which is almost the same thing. But can anyone see any way in which these are not the same, or like any? To be honest, most of the time, for most graphs H, these are exactly the same, but occasionally it's not. See any issue here? It's super subtle, but if the chromatic number of H is 2, then these are not the same. So this one was actually wrong. So just to kind of correct that, it should look like this. Right? Because if chromatic number is 2, what I'm saying here is that the extremal number is little o 1 times n squared over 2, which just means chromatic number, or sorry, the extremal number is little o of n squared. If the chromatic number is 2, I'm saying the extreme number is 0. It's like multiplying by 0, because that'll be a 0, right? 1 plus little 1 times 0, so it's just 0. It's technically not quite correct. But if the chromatic number is at least 3, then these are the same thing. It doesn't make a difference. Any questions about the statement of this? Do we remember what the chromatic number is and stuff? Okay. Okay. So yeah, so we're going to start proving this today and finish it on Tuesday. One thing, one way you might want to try to prove this is just by following the same approach that we did for Theorem's theorem. delete vertices, clone vertices, but that's not going to work because what we use for trans theorem is if I clone a vertex, if I didn't have a KR before, I can't have a KR now. But if you clone a vertex, you may create a copy of H when there wasn't one before, if H is a different graph, not a clique. So that's going to be a problem. So we have to get our hands dirty and do this a different way. Let me actually give you another equivalent statement of this. Well, maybe we'll do several of them. So the Theorem density of a graph H is some quantity we define by, so it's pi of H and when I say density, what I mean is basically we're asking what fraction of edges, so out of all the possible edges in a graph on n vertices, what is the largest fraction of edges that can be contained in an H-free graph? So it's like the extremal number of H divided by n choose 2. And we take the limit as n goes to infinity. So to clear what this is measuring, this fraction is kind of a natural thing to look at, right? Because it's saying I've got the max edges in an H-free graph, the extremal number, and I'm thinking of that as a percentage of the total number of edges in a complete graph, which is the maximum in any graph, right, on n vertices. So yeah, I'm just taking that limit as n goes to infinity. It's a nice exercise to show that the limit actually exists. So, because yeah, you'll remember from like analysis or something, you can't just like, or calculus, you can't just write limit and just say, oh yeah, that's what, limits may not exist. They may fluctuate or do some weird things as n goes to infinity. But actually the limit does exist for this. As an example, right, if I took the trend density of K3, actually maybe I'll leave that to the audience. So like, can anyone see what that's going to be? Including people online, if anyone, does anyone see what would the trend density of K3 be? Well, I'll give you one hint that the extremal number was the floor of n squared over 4. That was from Mantle's theorem. Yeah.
Is it 1/2?
Yeah, exactly. Yeah. I think you guys were at the same time. Right. Yeah, that's 1/2 because, I mean, we're taking the limit as n goes to infinity of basically, I mean, okay, I'll write the floor, but n squared over 4 floor over n choose 2. And like the top of the fraction is like basically n squared over 4. The bottom's like basically n squared over 2. For 1/4 divided by a half is half. So yeah. So what the Erdős theorem is saying is that so I guess the kind of restatement for any graph with at least one edge we can exactly compute this Terran density, and it's just going to be equal to chromatic number of H minus 2 over chromatic number of H minus 1. Because if I take this quantity and divide by n choose 2, it's basically the n squared over 2 cancels. Like, it doesn't quite, so I'm aware that, n choose 2 is n times n minus 1 over 2, but that is pretty much the same thing as n squared over 2. And if we're talking about everything in an asymptotic sense, yeah, that's not really any different. Okay. Any questions about any of this so far? Okay, let me tell you what we're actually going to prove. And we'll see, it should be fairly easy to see why this implies the Erdős theorem. Well, actually, maybe before that, I should say, first of all, the lower bound in this theorem is fairly easy, right? So for the lower bound, let G be a complete chi of H minus 1 part-type graph with parts of basically equal size, except for divisibility. So you have the n over the floor of, the floor of n over chi of H minus 1, or the ceiling of n over chi of H minus 1, where n is the number of vertices. So yeah, this graph cannot have a copy of H. The reason being, look at the parts of this graph and color them. You color each part with a different color. That's chi of H minus 1 colors. If there was a copy of H in G, then that coloring would give a coloring of G with chi of H minus 1 colors, right? And if we wanted to count the number of edges here, well, let's just do a lower bound even. So suppose I wanted to pick 2 distinct parts. How many ways are there to do that? So I'm just going to select, well, okay. I guess it's not clear whether I'm talking about like an ordered selection or an unordered selection, but this is what I mean. If I choose 2 parts, I've got chi of H minus 1 choose 2 ways of doing it. And between those 2 parts, actually, so let's say both parts end up being on the small end. They're both n over chi of H minus 1. How many edges would I see between them? So yeah. How many edges live in there? Yeah. Take whatever the size of those 2 parts are, and well, take the size of this part times the size of that part, which is, yeah, that thing times, that thing squared, right? Because, so in a complete multi-part-type graph, you've got all the possible edges. So the number of edges is equal to the number of ways to pick a vertex here and pick a vertex here, which is just, yeah, the size of that times the size of that. So we've got that. So I want to think of this like, so, well, okay, maybe I'll write things out a little longer. So and then on the bottom, I've got basically this, and on the top, I've got an n squared. And then I'm just going to say minus some kind of little o of n squared. The thing is, like, if you round this down, it'll subtract 1 from it at most. And then if you multiply things out, yeah, you will have some kind of small order subtraction here. Then we cancel things, and oops. Yeah, so you've got the right number of edges. Maybe I should make it clear that when I'm writing this kind of plus big O or little o1, it could be like, what I mean by this is like maybe this constant in front is slightly larger than this, but like it could also be slightly smaller. Like, so a plus little o thing is the same as a minus little o thing in some sense. Like, we just mean that the limit, like if I divide this by n choose 2 and take a limit, it will converge to that number. And that's what we mean by the little o thing. So actually, yeah, just to really drive this home, why don't I put the little o1 inside? I don't know what people's level of comfortability is with like asymptotic notation and stuff, but yeah, once you see things a few times, it might become clear. Any questions about this construction? Okay. So okay, so let's get into the proof. So one potential difficulty here is that there are a lot of graphs. Like, how do I have a strategy that is going to apply to every graph H? But if you think about it, you don't actually really need to deal with like any possible graph H. You can simplify your life a little bit. So let me kind of write down an equivalent formulation. Of the theorem, or at least the upper bound part. So we've done the lower bound. We just need to do the upper bound. So for all, let's say r at least 2, t at least 1 integers, and epsilon positive. So epsilon's a real number. There exists some number n naught depending on r and t and epsilon. Such that if n is at least this n naught of r, t, and epsilon, And G is a graph with the number of edges in G being at least this r minus 2 over r minus 1 plus epsilon, I should say n vertices, and at least this many edges. Then G contains a copy of the complete R-partite graph, K, T, 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 dot, 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 T, with, R parts. Give you a second to write that down and digest it. So before we were talking about any graph H, and now I'm claiming all I care about, like we only need to care about this type of a graph, just like we need to find copies of a complete R-partite graph. Yeah.
So what is T in this formula?
So T, well, we're going to prove this for all possible choices of R and T. I guess I'm not sure if your question is what's the relevance of T, but maybe I'll kind of ask you guys. Can you see, like, why is this sufficient? Like, why? Because all I'm saying is you can find a copy of this type of graph, and why does that mean you could find like a general graph H? That'll kind of tell the relevance. Oh yeah. Yeah, if T is big enough. Yeah, right? Because if I have a graph of chromatic number R, think about a coloring of it with R colors. Each color class has some size. If I pick T to be bigger than that size, then if G contains one of these, it'll contain H. So in particular, like to be a bit sloppy about it, so if G contains this K, T, T, dot, 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 R of them, then it contains every H with chromatic number equal to R and number of vertices. And this is where I'm being a bit sloppy, but like what I'm saying is true, right? If the number of vertices is at most T, then if you were to color it with R colors, all the classes will be at most T. And so, it'll be contained in that thing. That seems like a sort of natural thing to write down. Although that statement wouldn't be quite true, because what if every coloring of H has if H has R times T vertices, the coloring may not break it into classes of size T. One of them might be bigger than T, and then you can't find it in this graph. So, but certainly, if I color H, if H has at most T vertices, all the color classes will be size at most T. So we could have replaced this with saying it has chromatic number R, and there exists a coloring in which every color class has at most T vertices. But I was lazy, I just say it has at most T vertices. Yeah?
Is this actually equivalent? Like, can we get this out of the other one?
Yeah, because you could just let H be that graph. Maybe the thing that might be a little bit unclear is this dependency on T or something in the.
Yeah.
Yeah, but the original theorem, so the idea is you fix an h, and then if n is large enough with respect, and you fix an epsilon, so that kind of deals with the little o1. You fix an h and an epsilon, and if n is big enough with respect to h and epsilon, then the extremal number is at most, this with this thing. So choosing n big with respect to r and t is the same as choosing it big with respect to the graph h. Like if this is the graph h, because yeah, r and t determine the graph. So yeah, it is the same statement. Any other questions? So yeah, this kind of clarifies what we're trying to build here. Okay, so, but yeah, there's kind of an inherent, there's lots of challenges here. Like I said, we can't just do what we did last time. We can't clone vertices, because definitely, you could have k t t t t t t minus 1, and then I clone a vertex, and it makes one of these things, right? That's going to screw things up. So yeah, we've got to find this without doing that kind of operation. And like, it becomes kind of hard to know where do you look. Like, I have a graph, and all I know is that the global edge density, like the global number of edges, is big. If I pick a location in the graph and I say, okay, this is where I'm going to start building, I'm going to start making this subgraph there. Well, why won't you just run out of edges there, and maybe the edges are all over there? You have to somehow find the best place to start building this graph. You don't want to start building it and run out of edges. Okay, which I think that does make it kind of hard. But so sort of a crucial idea here is that what we're going to do is we're going to actually just throw away most of the graph G. We're going to be left with a small subgraph. But we want that small subgraph to have large minimum degree. So I want this subgraph, everything in that subgraph to have high minimum degree. If that's the case, then if you think about it, you can't really go wrong. You start building in that small subgraph. Everywhere you go, every vertex I pick is going to have, it's not going to be deficient. It's not going to have low degree. So it kind of helps you keep building the graph. So let me formally say what I mean by finding this graph of large minimum degree. So first, a quick definition. Delta of G, little delta, is the minimum degree of a vertex in a graph. So minimum among all the vertices. We're not going to use this here, but I'll just write it down because I may as well at this point. So capital delta of G is the maximum. Okay. So let me get this right. So pick some number alpha between strictly bigger than 0, but less than or equal to 1. And let G be a graph with n vertices and where the number of edges is at least alpha times n choose 2. So I'm just kind of quantifying like what is the density of this graph, basically. What percentage of the edges does it have? So then for any gamma between 0, strictly between 0 and alpha, there is a subgraph G prime of G such that, so apologies, but I'm going to put this on the next board. So the minimum degree in G prime, so yeah, remember I've got this gamma which is less than alpha. So what I'm going to say is that if I, well, let's just see what it says. So it's at least gamma times the number of vertices in G prime minus 1. Okay. And I want to also say that, like, by trying to find this graph G prime, I haven't thrown away everything. We're going to throw away most of the graph, but I want there to be something reasonable left over. Certainly, I don't want to end up with a graph on one vertex, which, by the way, this would be satisfied if I had a graph on one vertex. So I don't want some trivial, stupid thing to happen, right? So I want the number of vertices in G prime to be at least n times the square root of this fraction alpha minus gamma over 1 minus gamma. And in some sense, it doesn't really matter what this is, but this is going to be a number between you know, 0 and 1. So, and it only depends on alpha and gamma. It doesn't depend on n. But if gamma is really close to alpha, this could be really close to 0, right? So essentially, the number of vertices left in G prime could be n times, yeah, n over 10 to the 10 to the 10. But yeah, it's not 0, or it's n times something. Any questions about this statement? Okay. Yeah, so basically I'm saying so I would love, what I would actually really love to have is a graph where the minimum degree is like alpha. Like I'd like G to have minimum degree alpha n minus 1. That would be quite nice. I can't have that, but what I'm basically saying is if I relax that a little bit by any kind of small amount, I can find a subgraph which does have, you know, that kind of relaxed degree condition. But it might have very few vertices, but it's still, I mean, it's not that few because it's still a constant times n. Okay. So let's prove this. So this is going to be like kind of a iterative process. We're going to start with G, and we're going to delete vertices until we get G prime. But like, okay, now I'll ask you to just tell me what the algorithm is, essentially. Like, suppose I'm telling you that what we're going to do, we're going to start with G. I'm going to 1 by 1 delete vertices until I get G prime. Which vertex do I delete first? Yeah, because like, what else would I do, right? Because, I mean, if I don't delete that one, it's still going to be there, and it's still going to have small degree. If I want to make my minimum degree large, kind of the only reasonable, sensible thing to do is to delete the smallest degree, because if you don't, it's still going to have small degree. It might even get smaller if I delete one of its neighbors. right? So yeah, so that's what you want to do. So I'm going to let G naught, so G0 is G, and for I at least 1, let Gi be obtained from Gi minus 1 by deleting a vertex of minimum degree. And we're going to stop this process when the minimum degree of Gi is at least gamma times the number of vertices in Gi minus 1. So the first time, it kind of makes sense, right? That's when I would stop. Because if this thing is satisfied, then at least I've got that condition. And then why would I keep going? Because like if I keep deleting things, it's not going to help me satisfy this. It's going to give me fewer vertices. So sensibly, like the first time you should stop. Like when you see this condition hold, you should stop. You should not keep going because you're going to have fewer vertices. Now, a reasonable thing to ask here is like, why would that ever hold, right? But it does hold at the end. So when you have one vertex, this is 0, that's 0. So it does hold at the end. So yeah, or I mean, the end is kind of when that holds. But like if you were to delete everything but one vertex, it would hold. So it does eventually hold. So there is a first time when we get this. Is that clear? Okay. Okay, so we just need to show that the final graph Gi satisfies this second inequality. So let's say how many, before I estimate the number of edges in Gi, or sorry, the number of vertices, let's say something about the number of edges. So the number of edges will be however many edges we started with minus the minimum degree of G0 minus the minimum degree of G1 minus ... minimum degree of G I minus 1. Because that's how we defined it. We always delete the lowest degree. And actually, I can say something about these minimum degrees. Because the thing is, if, let's say, the minimum degree in G0 was large, whatever I mean by that, we wouldn't have done anything, right? If the minimum degree of G0 satisfied like this kind of condition, we wouldn't have deleted anything. So it must be smaller than the analogous thing here. So this is strictly larger than taking what I started with, which, by the way, we can let's substitute this as well. So the number of edges in G0 is alpha times n choose 2 at least, and then all of these numbers are all less than gamma So V, number of vertices in G0, minus 1, minus gamma, number of vertices in G1, minus 1, minus dot, 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 number of vertices in Gi minus 1, minus 1. Okay, so, well, these terms, I mean, the way I've written it is almost cryptic, right? Like, I mean, how many vertices does G0 have? It's n, right? And then this one's n minus 2 down to gamma times n minus I minus 1 minus 1. So I think n minus I. Okay, so let's keep going. So, so this is like a one of those, like, you know, like the sum of I equals 1 to n minus 1 of I, right? That should be n choose 2, or in other words, like n times n minus 1 over 2. That's kind of like one of those, except it's kind of two of them subtracted, right? So this should be gamma n choose 2, and then plus gamma n minus I choose 2. So this is the sum of the first n minus 1 integers minus the sum of the first n minus I minus 1 integers. Does that make sense? So yeah, I want to, you know, yeah. It's like sum of j equals 1 to n minus 1 minus the sum of j up from, you know, from 1 up to n minus I minus 1. And yeah, that becomes this. So I also want to do, let's do a really kind of stupid upper bound on the number of edges in GI. And the stupid upper bound is it could be all of them. I don't know. I mean, and how many edges or vertices does GI have? It has n minus I think. Okay, so we've got an upper bound and a lower bound. And then we're going to somehow put these together to get a bound on I, which will tell us how many vertices GI has. So yeah, these are two different things, right? So yeah, number of edges is bigger than this, smaller than, or at most n choose I, n minus I choose 2. So then what we get is, okay, what are we going to do here? This part is just really moving around stuff. Yeah, okay, so if we put these two things together, we've got an n minus I over n minus I choose 2 on both sides, kind of, but this one has a gamma in it. Put those on the same side. So and yeah, so put all the n choose 2s on one side and all the alpha minus gamma. No. Yeah. So I'll write this like this. So So I haven't written what we have over there yet. I've just kind of written, I'm just kind of estimating. So n choose 2 is at least n minus 1 squared over 2. So this should be true, and this is positive. And by the thing we have over there, this is less than 1 minus gamma n minus I choose 2. Which is less than or equal to 1 minus gamma n minus I squared over 2. At this point, it's just a lot of algebra. So I'm just kind of now canceling the 2's and writing this inequality down. Okay, and maybe at this point, you can take my word for it. If you solve for I, maybe you might have to throw away some small terms or something. But essentially, if you solve for I, you get that I is less than n minus square root alpha minus gamma over 1 minus gamma times n minus 1. Oh, and then, sorry, at the end there's a plus 1. Which, if you kind of plug that, because remember, GI has n minus I vertices, so yeah. So this is a strict inequality, but there's a plus 1 that kind of gets rid of the plus 1 in some sense. So in any case, so yeah, the number of vertices in GI turns out to be at least square root alpha minus gamma over 1 minus gamma n minus I minus 1. But each of these steps is really just algebra. And that's the number of vertices in GI minus 1. So it's what we wanted. In some sense, these final algebraic details are not really the main point of this. But yeah. If you want to know exactly how they go, you could look in the notes. But you could also just expand this and figure it out yourself. It's not too bad. I mean, basically square root both sides, right? And now I've got n minus I. I could solve for I. In fact, you could solve for n minus I. That might be faster. Because what I really want is kind of want n minus I minus 1 or something. Anyway, square root both sides, manipulate it, and it works out. Okay, so this means, kind of to recap, what we can do is if I've got a graph with high edge density, I can find a small part of it that has high minimum degree, and then we're going to work completely in there to try to construct our complete multipartite graph. Okay. Questions or anything? Yeah.
Yeah, so why is that good enough? Because we want it to be n. What's that?
In the end, we want it to be whatever the number of vertices in G prime is, and G prime will be GI.
No,
Oh.
I mean the vertex one.
Yeah, you're right. I think I probably wrote this down wrong. Yeah, I think I have written this down wrong. It will be n minus 1. Yeah, sorry. If you see, there's not going to be any i's in, like, this will be n minus I when I pull that over, and yeah. Or sorry, put that over there, put that over there.
It's still n minus 1 though.
Yeah, but still n minus 1. It's possible I may have written this down wrong as well. I'm not. Well, in any case, that wouldn't matter either, because actually, yeah. The only thing we care about here is that we haven't eliminated all the vertices. Like, there's still, like, if n is large, there's still a large number of vertices left. It wouldn't actually matter what's there as long as it's not like 0 or like we have 1,000 vertices left. It has to go to infinity as n goes to infinity. That's the only thing that matters. So that would be fine as well. Check the notes. Maybe there might be a mistake in there, but yeah. Morally speaking, this is what you want.